we're going to look for groups of functions that will help us with our idea of determining convergence and divergence of these areas in the plane. So we talked about we have direct comparison with other functions, we have limit comparison with other functions. So if we know about convergence or divergence with an entire group of functions, those functions would really help us when it came to direct comparisons or limit comparisons. So here's a whole set of functions that it turns out it's really easy to determine whether this type of function converges or diverges. So if we have a function of the form 1 over x raised to the power of p, there are some things about p I want to make clear. P has to be a positive value. For now, p is not equal to 1, and I'll explain that in a minute. If we have the function of the form 1 over x to the positive p, we can rewrite that equivalently using algebra as x to the negative p. When we have an improper integral, we can't talk about doing anything unless we introduce the limit. Now we can find the antiderivative, and we can do fundamental theorem. Well, this is just a power function. The power rule is 1 over the power plus 1, x to the power plus 1, plus c. But we're doing it the definite integral, so you can see fundamental theorem notation at the end. That's where that comes from. So when we actually evaluate and do fundamental theorem, upper limit minus lower limit, we can determine some things about this type of function. The first thing we can determine is that the second term, the lower limit, will just result in a real number value. The first term is the term that taking b to infinity is going to affect. And it turns out that inside this limit, as b approaches infinity, if b winds up in the numerator of that fraction based on the value of p, then when we take b to infinity, that area will diverge. If b winds up in the denominator of that fraction based on the value of p, then that limit's going to 0, and that area will converge. So since p is in the driver's seat, then all we really have to determine for convergence and divergence is the value of p. If p is less than 1, remember, it has to be positive. If p is less than 1, then the result of negative p plus 1 is going to be a positive value. As we take b toward infinity, that's the case where b is in the numerator, that area must diverge. So simply by inspection, we're going to look to see if p is less than 1. If p is greater than 1, the result of that exponent will be a negative exponent. This will give us b to some negative value, which is equivalently written as 1 over b to some positive value. As b tends toward infinity, this term tends toward 0. That's what convergence looks like. So simply by inspection, determining whether p is greater than or less than 1 is going to allow us to determine divergence or convergence. Now there is a third case where p equals 1. That's this case here. The limit as b approaches infinity from 1 up to b of 1 over the square root of x squared minus 0.1 dx. Well, this is not a straightforward u substitution. I think we very quickly see we run into variable trouble right away. So not something we can do by hand. So let's see if this whole idea of P will help us. We do realize that convergence or divergence, we said this in the last set of videos, doesn't happen near the origin. It happens near infinity. I don't care how big x gets. Subtracting 1/10 from x squared for large input values, as input values tend toward infinity, is not making a difference in the heights of our rectangles. Not an appreciable difference. It's going to show up in an accumulated area anyway. So this function technically should do, as far as convergence or divergence is concerned, what this function does. Now, all I did algebraically is clean up the square root of x squared. Some of you are not going to like the fact that I did not get absolute value of x, but where am I in the plane? Nothing but positive values of x going in that function. So I'm going to drop absolute value. We know we can do fundamental theorem on this function. The antiderivative is the natural log of x. Not a problem for us. Notice I'm really meticulous about writing that limit notation down at every single step. Although natural log is a very slow-growing, excruciatingly slow-growing function, it's still a growing function. This term is headed toward infinity. This term we know has a value of 0. So this function is diverging. That is the case, by the way, where P is 1. So we could go back here that when P is less than or equal to 1, our area diverges. We just proved that. Now, I'm not through. What I've done is I've done a really good job of showing that that function diverges. I haven't really actually shown that that one does. That's where the whole direct comparison, limit comparison idea comes into play. They have asked me what this unknown function does concerning convergence and divergence. I have determined what this function does. It diverges. Now I have to do some comparison. I could do the limit comparison, the limit as x approaches infinity. Remember our known function, which I'm just going to call x. Our known function goes in the denominator. Our unknown function is our numerator function. It may not be a pretty limit to evaluate, but it's still a limit we can evaluate. Remember, I'm just using algebra on this step. This is infinity over infinity. I could use L'Hopital's, but please tell me that you remember when a root shows up, L'Hopital's isn't going to do anything but bounce that root from numerator to denominator to numerator to denominator every step of the way. So I'm not really going to use any algebra to manipulate this limit. I'm just going to realize that for large input values, the denominator function acts like that. And I'm going to show the AP reader that I recognize that. You can't go from this step directly to this one. Directly to this one. You have to show them that you recognize this is what you're doing. So show either of those two relationships to the AP reader if it was a free response question. Remember, we have three results coming out of our limit comparison. This result, 0, says the numerator function is smaller than the denominator function. Remember, we found that the denominator function diverges over our interval. So that would not help us. Plus, we didn't get that. We got 1. So here's our result. And when we get any real number value, not 0, the limit comparison tells us that the functions behave the same, alike, however you want to write it. And I would need to say, since this area diverges, then by, we could call it limit comparison. We could just say comparison, but we use the limit, and there is direct comparison. By limit comparison, the unknown function they ask us about must also diverge. So not difficult. None of this is difficult. But that's what it looks like to use some known function to determine what's happening on some unknown function. We're going to use the idea of determining what happens to a function based on the value of p, and then we're going to have to show the comparison between what we chose as our comparison function and the unknown. So here is a known area. Since p equals 2 and 2 is greater than 1, then this area converges. That's all I need to do to show. I don't have to find the antiderivative. I don't have to plug in and show fundamental theorem. This, referring to a value of p and making a comparison with that value and 1, is enough for me to say I know this area converges. But there's one more step. I have to do either a direct comparison or a limit comparison, putting my unknown function in the numerator, my known function in the denominator, using excellent algebra and calculus. I need to evaluate that limit. And it's perfectly fine, since I'm near infinity, just to go directly to 1. But I have to communicate to the AP reader that I know what that result means. Since this area converges by, again, I did a limit comparison. This area must also converge. Simple as that. Not difficult, just different. Let's stop the video here. We'll move on to the last couple of examples in the next video.